In this video, I introduce a masked visual pre-training for video prediction. Masked video transformer is a foundation world model that is used to generate videos by pre-training transformers via masked visual modeling. Masked VIT predict future visual frames conditioned on past observations and motor commands so that the embedded agents can plan solutions to a variety of tasks in a complex environment. MaskViT is trained using a two-stage procedure. First, the encoding of the visual data that tokenizes input video into latent tokens based on a discrete variational autoencoder. Second, pre-train a bidirectional transformer with window-restricted attention via MVM, as shown here. This input video with T frames, this encoder, this context tokens, this partially masked tokens. This is the bidirectional window transformer, this spatial window attention, and this spatial temporal window attention block. This T-1 generations. Since a video contains too many pixels that cannot be used as tokens in transformer, vector quantization variation autoencoder is trained to map each input video frame to a small number of discrete tokens. As shown here, this input frame, this encoder, this lookup table, and this decoder that reconstruct the image from the latent tokens. For example, each input video frame is individually tokenized into a 16 by 16 grid of tokens as shown here. MaskViT is pre-trained via MVM. The latent codes corresponding to the context frames are kept to be intact, and a random number of tokens corresponding to future frames are masked. MaskViT model is trained to predict the masked latent tokens conditioned on the unmasked latent tokens and the context tokens. Using the context frames for TC time steps, MVM predicts the TP frames during test time. The entire video sequence are first tokenized into latent tokens Z. ZP denotes the latent tokens corresponding to the future video frames, where N is a dp by h by w. A variable masking rate is used to reduce the gap between the pre-training task and the inference. During training for each video in a batch, a masking ratio R is used to randomly select the masking tokens and replace R by N tokens with a mask token. The pre-training objective is to minimize the negative log likelihood of the visual tokens given the masked video as an input, as shown here. Where D is the training dataset, NM represents the randomly masked positions. ZPM denotes the output of applying the mask to ZP, and ZC is the latent tokens corresponding to the context frames. All masked tokens are predicted condition on all unmasked tokens. As shown here, this mask visual modeling, this input video, this encoder, and this context tokens, this partially masked tokens. Bidirectional window transformer uses two types of non-overlap configurations. First, Spatial window restricts attention to all the tokens within a subframe of size 1 by h by w. Second, spatial temporal window restricts attention within a 3D window of size t by h prime by w prime as shown here. This SW block and this STW block. SW and STW attention blocks are sequentially stacked to, again, both local and global instructions in a single block. A small window size here is sufficient to learn a good video prediction model while significantly reducing memory requirements. Since it's time-consuming to decode tokens autoaggressively, a non-autoaggressive decoding model predicts future video frames, namely predict videos in t steps where t is much smaller than the total number of tokens to predict. Gamma t is a masking schedule function where t is sampled from here, which is chosen so that it's monotonically decreasing with respect to t, and it holds gamma 0 tends to 1 and gamma 1 tends to 0 to ensure convergence. At t is 0, start with z, where all tokens in zp is masked tokens. For the next iteration, n tokens are masked out by keeping previously predicted tokens and the most convenient token predictions in the current decoding step. As shown here, this is the gamma 6 scaling gamma functions as shown here. And here is SVD scores of 6 scaling functions. High SVD score means poor video generation. For more details, please check with these references. Thank you. Bye.